Hello friends, welcome back to my YouTube channel. Today I'll be discussing a numerical based on design of storage vessels. So in my earlier few videos I have been discussing various aspects of design of storage vessels. You can go and watch those videos. I'm giving links to those videos in the description section. So today we will understand how to design a storage vessel with a fixed self-supporting conical roof. So one numerical will be discussed. I'll be discussing one numerical that will help you understand the design process. Now let us look at the numerical statement. Design a fixed conical roof tank using the following data. Data is given to us. Tank internal diameter is given, it is 20 meter. Tank height is given, it is 12 meter. Specific gravity of the liquid is given, it is 1. Specific gravity of the liquid in the tank is given, it is 1. Permissible slope for the conical roof is given, it is 1 in 5. Superimposed load that is acting on the roof, it is given to us, it is 125 kg per meter square. Permissible stress for the material of construction is given, it is 1420 kg per centimeter square. Density of the material of construction is given to us, it is 7700 kg per meter cube. Modulus of elasticity for the material of construction is given, it is 2 into 10 to the power 6 kg per centimeter square. A well joint efficiency factor is given, it is 0.85. Shell and bottom plate size is given to us, it is 6300 mm by 1800 mm. So the shell will be constructed using rectangular plates, and for each plate the size is given to us, it is 6300 mm by 1800 mm rectangular plates. So same plates will be used for construction of bottom as well. Then Poisson ratio is given, Poisson ratio is 0.33. So with this data we are supposed to design a storage vessel with a fixed conical roof. So we will design that storage tank. Let us do that. Okay, now let us know what are the steps involved in the design. First we have to design the shell. So first step will be design of the shell, and over here you are going to calculate internal load, that is PI. Then for this internal load we need to calculate pH, that is hydrostatic pressure first, so that we have to do. Then after you calculate pH, uh, using pH you are going to calculate PI. Now this tank, if you look at the data that is given to us, they have not mentioned about any internal pressure, so we are going to consider it as non-pressure tank. So for non-pressure tank, PI, the internal load, is nothing but the hydrostatic pressure, that is pH. So first pH has to be calculated, then after pH is calculated, which is PI in this case, using PI the thickness of the shell will be calculated at various heights. Then second step is design of fixed self-supporting conical roof. Over there we are going to calculate thickness for the given slope. And last step in the design is design of flat bottom, where again we are going to calculate thickness for the plates that will be used for constructing the bottom. Okay, so let us start with design for the shell. So first we will be calculating pressure at the bottom of the tank, that is we are calculating pH, hydrostatic pressure. So let me show you a simple schematic for the tank. You have the tank with conical roof. Height of the tank is 12 meter. Diameter of the tank is 20 meter. And for calculation of pressure, it is assumed that tank is filled with the liquid to its full capacity. That means height of the liquid in the tank is 12 meter. Now the pressure is given by this formula. pH is equal to rho into H minus 0.3 into G. So why this equation? Because as per standards we are supposed to calculate hydrostatic pressure at a distance of 300 mm from the base. Okay, so if you are doing it doing the calculations at the bottom, so you'll be considering a point that is 300 mm above the bottom. So that's why we are considering height to be H minus 0.3. So I have discussed all this in my earlier videos on design of storage vessels, so please watch them. Now in the data it is given that the specific gravity of the liquid is 1. That means the liquid is nothing but water. So the liquid is water. And for water you have density as 1000 kg per meter cube. Height of the tank is given, it is 12 meter. G is 9.81 meter per second square. Acceleration due to gravity. Okay, so therefore when if you use this equation, it will be pH is equal to 1000 into 12 minus 0.3 into 9.81. So after simplifying, we'll be getting pH as 114777 Newton per meter square. Since we have considered it to be non-pressure tank, it is a non-pressure tank, pH will be equal to Pi, and Pi is going to change with height. You know, the internal load Pi is going to change with height of the tank. Okay, now let us continue with our calculation. First, with the calculated Pi at the bottom, we are going to calculate thickness of the shell. Thickness at the bottom will be calculated. It will be given by this formula: Ts is equal to Pi into di upon 2Fj minus Pi. Pi we just calculated, it is 114777 Newton per meter square. Di is 20 meter given to us. F is 1420 kg per centimeter square. You need to convert it to Newton per meter square. So it will be 1420 into 9.81 Newton and into 10 to the power 4 per meter square. So that will give us F as 13930.2 into 10 to the power 4 Newton per meter square. J is given to us, it is 0.85. Ts, after putting all the values in this equation, you get Ts is equal to 114777 into 1020 divided by 2 into 13930.2 into 10 to the power 4 into 0.85 minus 114777. So after simplification, you get Ts as 9.70 into 10 to the power minus 3, that is 9.70 mm. So corrosion allowance, they have suggested to use a corrosion allowance of 2 mm. So after adding the corrosion allowance, you get Ts as 9.70 plus 2, that is 11.70 mm, and we are recommending a thickness of 12 mm for at the bottom. Okay, now next we will find number of plates. Now by number of plates I mean we are going to find out number of plates in one layer, where you know different layers are used for constructing the shell. So in a single layer there will be number of plates. So here the task is to find out number of plates in a single layer. So metal plates, these are welded in layers. Plates in a layer, they are vertically joined by butt weld joints. So plates, they are vertically joined by using butt weld joints. To facilitate welding, a gap of 2 mm between adjacent plate is desired. So in order to have better welding, in order to facilitate welding, a gap of 2 mm is given between two adjacent plates. So you can see that in the schematic diagram. So this is the bottom of the vessel. Now you have arranged one plate, then adjacent to that plate you have arranged another plate. In this way, number of plates are arranged to form a single layer. Now what you are seeing is the bottom layer. So you have number of plates in the bottom layer, those are arranged, and in between two adjacent layers a gap of 2 mm is left. What is the reason for that? The reason is to facilitate welding of the plates. Now for each plate the length is 6300 mm, whereas width is 1800 mm. So each of the plate will be having a length of 6300 mm and a width of 1800 mm, and we need a gap of 2 mm in order to facilitate the welding process. Now if you say that there are n number of plates in a layer, in a single layer, if you say that there are n number of plates, then you will have this equation. You just carefully look at this equation. Now pi into di plus ts, internal diameter of the shell plus thickness of the shell. So this will give you equivalent diameter. Equivalent diameter into pi, this will give circumference of the vessel, circumference for the shell, pi into di plus ts, internal diameter plus thickness. This will give you circumference, and from this circumference we have to left out this a gap of 2 mm. For each plate there is a gap of 2 mm, that is 2 into 10 to the power minus 3. Therefore entire circumference minus gap for n plates, that will be number of plates into gap for one plate, gap between two adjacent plates, which is 2 mm, that is 2 into 10 to the power minus 3. So this entire circumference for the shell minus gap left for facilitating welding, this distance will be equal to number of plates into length of individual plates. So you have to use such a number that you get this distance, total circumference minus gap left for facilitating welding. I hope you have understood the equation. If you have any doubts, you please mention that in the comment section. Length is given to us, it is 6300 mm. Okay, now let us continue and find a number of plates in one layer. So I have already said if n is the number of plates in a layer, then you have this equation, pi into di plus ds minus n into 2 into 10 to the power minus 3, that is equal to n into L. L is given to us, it is 6300 mm. So if you put all the values, this will be pi into 20 plus 12 into 10 to the power minus 3 minus n into 2 into 10 to the power minus 3, that is equal to n into 6.3. Thickness we just calculated, thickness at the bottom is 12 mm, including corrosion allowance. So you have this equation. If you solve this equation, you are ultimately going to get the value of n, and if you solve it, you will get a value of n, and value of n will come out as 9.97. N will be equal to 9.97, that is approximately 10 plates. That means in one layer there will be 10 plates of the size 6300 mm by 1800 mm. So at the end of this particular calculation, we now have got a number of plates in a single layer. So let us continue with our discussion. Now we are going to find number of layers. How many layers are required to form a shell with height of 12 meter? Now let us do that calculation. So number of layers. Height of the tank is 12 meter. Height of a single layer is 1800 meter. So you can easily understand this. So for that, so this plate, if you look at a single plate, the plate can be shown like this. This distance is 6300 mm, and this distance is 1800 mm. So now in one layer will be having a height of 1800 mm. So how many such layers will be required in order to construct a shell which has a height of 12 meter? That is what we are going to find out. Therefore number of layers will be equal to, number of layers is equal to 12 upon 1.8. Total height is 12 meter, height of individual layer is 1.8, so that is going to give us a number of layers as 6.67, which is approximately 7. So you can see that in the schematic diagram. I'll just erase this so that you understand it in a better way. So now you can see the storage tank. This is the first layer. And what is the height of this first layer? Height is 1.8 meter. Okay, so you need another 6 such layers, 6 layers of height 1.8 meter each. So ultimately the shell for the storage vessel will be constructed with 7 layers whose heights are 1.8 meters. Okay, so there will be 7 such layers. For each layer the height will be 1.8 meter. Okay, so this is the first layer, second layer, third layer, fourth layer, fifth layer, sixth layer, and seventh layer. So the entire the shell will be constructed by using 7 layers. Okay, so that means now we know we have calculated a number of layers that are required to construct the shell. Height is 1.8 meters, so I have talked about it. Now what is our task? Thickness of the shell is going to change with height. What is the reason for that? Internal pressure, pi, changes with height. So if pi is changing, thickness will also change. So let us begin with let us calculate thickness of plates in various layers. Plate thickness is different in different layers. We have understood that. Thickness of plates in the lowest layer we have already calculated just now, it is 12 mm. Now thickness is lesser for higher layers. So as you move from layer number 1 to layer number 2, 2 to 3, 3 to 4, so and so forth, the thickness is going to decrease. So you'll learn how the thickness decreases. Okay, so let us continue with our discussion. Uh, for the first layer, that is for bottom layer, we have already calculated the thickness. The thickness is 12 mm. Now let us calculate thickness for the second layer. Now for calculating thickness for the second layer, you need to evaluate pressure at a height of 1.8 plus 0.3, that is 2.1 meter. And how is that? See, now you have done calculation for lower layer. Lower layer is having is going to have a thickness of 12 mm. Now we are supposed to calculate thickness for the second layer, and for that, as the theory suggests or standard suggests, pressure has to be calculated at a distance of 0.3 meter from the bottom of that particular shell course. So if you are doing calculations for second layer, second shell course, pressure has to be evaluated at a distance of 0.3 meter from bottom of the second layer, second shell course. So it will be 1.8 plus 0.3. That's why you have this equation over here. You have this height 1.8 plus 0.3, that comes out to be 2.1 meter, and this is now measured from the bottom. So if this is the case, then pressure for second layer, pressure will be evaluated as pH is equal to rho into h minus 2.1 into g. So total height minus distance from the bottom, that is 2.1. So if you put all the values, density is 1000, h is 12 meter, g is 9.1, you'll come to know that pH comes out to be 97,119 Newton per meter square. Now once pH is calculated, for non-pressure tank this is nothing but PL. So you can calculate thickness by using this formula. Ts is equal to pi di upon 2 fj minus pi. Pi is internal pressure. For non-pressure tank, internal pressure is equal to pH. So you simply put all the values. Pi, that is pH, we have calculated it. So if you put all the values, you get thickness as 8.2 mm, and when you add the corrosion allowance, thickness will be coming to be 10.2 mm, and you are recommending it as 11 mm. So thickness for the second layer, is 11 mm. Thickness for the second layer of the shell is 11 mm. Now let us move ahead. Let us calculate thickness for the third layer. Now you can easily, you are calculating thickness for the third layer. That means pressure will be evaluated at a distance of 0.3 meter from the bottom. So total height will be 1.8 plus 1.8 plus 0.3. So thickness for third layer, for that pressure will be evaluated at 3.6 plus 0.3. I have already explained over here. So the height will be 3.6 plus 0.3 is 3.9 meter. So this is measured from the bottom. Therefore, pressure will be evaluated as pH is equal to rho into h minus 3.9. It will be 3.9. It will be 3.9 into g. So pH will be equal to 1000 into 12 minus 3.9 into 9.81, and that comes out to be 79,461 Newton per meter square. Now, once pH, that is internal pressure, internal load is known to you, you can calculate thickness as thickness by using the formula. All values are known to us. You just have to put all the values. You put all the values. You have just calculated pH. pH is nothing but pi, the internal load in this case, and this gives us a thickness of 6.71 mm. If you add corrosion allowance to it, so this will be 6.71 mm plus 2 mm, that is 8.71 mm, that is approximately 9 mm. That means thickness for the third layer comes out to be 9 mm. For first layer it is 12 mm. For second layer we have calculated it as 11 mm. Now for the third layer it is 9 mm. Okay. Now let us do calculations for fourth layer, thickness for fourth layer. So you are calculating thickness for this layer, fourth layer. So total height involved will be 1.8, 1.8, 1.8. So 1.8, 1.8, 1.8, and for fourth layer you have to consider the distance of 0.3 meter. So for fourth layer, pressure is evaluated at 5.4 plus 0.3. So 1.8 plus 1.8 plus 1.8 is 5.4, and plus 0.3 for the fourth layer. So height involved will be 5.7 meter from the bottom. Okay. Now pressure will be evaluated as PH is equal to rho into H minus, now this time it will be 5.7 into G, that is pH is equal to 1000 into 12 minus 5.7 into 9.81, that comes out to be 61,803 Newton per meter square. So once pH is known, that is nothing but internal load, so you can calculate thickness. Thickness, you have the formula pi di upon 2fj by ns pi. All values are known to us. Pi is 61803, and all other values you can put, and you can get the thickness as, or you will get the thickness as 5.22 mm. After adding the corrosion allowance, thickness will be 7.22 mm, and you can recommend it to be 8 mm. That means thickness for fourth layer comes out to be 8 mm. Thickness for fourth layer it comes out to be 8 mm. For third layer it is 9 mm. For second layer it is 11 mm, and for the first layer it is 12 mm. Now let us do calculation for the fifth layer. Calculation for the fifth layer. Now pressure is evaluated for fifth layer. Now you are talking about this layer. Layer number 1, 2, 3, 4, 5. You are going to do calculations. Pressure will be evaluated at this point, 0.3 meter from the bottom of layer number 5. So in this process, the total distance involved will be, pressure is evaluated at a distance of 7.2 plus 0.3, that is 7.5 meter from the bottom. Okay. So therefore pressure is evaluated by using this formula. This will be rho into H minus, now this will be 7.5, H minus 7.5 into G. So if you put all the values, this will be 1000 into 12 minus 7.5 into 9.81, this comes out to be 47,088 Newton per meter square. So once pH is known, that means internal load is known, thickness is evaluated as pi into di upon 2fj minus pi. Pi is 47,088 into 20 divided by 2 into 13930.2 into 10 to the power 4 into 0.85 minus 47,088, and thickness after calculation you will come to know that thickness comes out to be 3.98 mm. Therefore thickness is 3.98 mm plus corrosion allowance of 2 mm. Total thickness is 5.98 mm, which is approximately equal to 6 mm. Therefore for fifth layer thickness will be 6 mm. For earlier layers it was 8 mm, 9 mm, 11 mm, and for the first layer it was 12 mm. Okay. Now let us do calculations for sixth layer. Sixth layer, that means you are talking about this layer. We are going to calculate pressure at a distance of 0.3 meter from the base of this layer. So pressure is evaluated at uh, what is the distance? It will be 9 plus 0.3. That is distance will be 9 plus 0.3 is 9.3 meter. Okay. And this will be done from the bottom of the vessel. Now pressure is evaluated uh, by using the formula you already know. Now you perfectly know what is the formula. In this case it will be 9.3 into G. So pH is equal to 1000 into 12 minus 9.3 into 9.81. That gives us pH as 26,487 Newton per meter square. Now once pH is known to us, this is nothing but internal load, that is Pi. Therefore you can calculate thickness as Pi di upon 2Fj minus Pi. After putting all the values, Pi you just calculated 26,487, and rest other quantities after putting you get thickness as 2.26 mm, and when you add the corrosion allowance, thickness will be 4.26 mm, which is approximately 5 mm. That means for the sixth layer, thickness is of 5 mm. Okay. Now let us do the calculation for the last layer, seventh layer. Calculation for the seventh layer. We did calculation for sixth layer. Now this time we are going to do calculation for seventh, or rather I have just written what, just let me rub it, erase it, just one minute. So we just calculated that thickness for sixth layer is 5 mm. Now the point is for storage vessels we need to have minimum thickness of 5 mm, and if you go and check for seventh layer you'll come to know that thickness is going to come below 5 mm, and that is not desirable. So we need at least 5 mm thickness. Therefore we are going to conclude that thickness for the last layer, even for this last layer, thickness will be 5 mm. That means for thickness for last two layers, layer number 6 and layer number 7, it will be 5 mm, because at least 5 mm thickness should be provided to the tank. So thickness of plates in various layers, now we have calculated. Lowest layer, that is first layer, it is 12 mm. For second layer it is 11 mm. For third layer it is 9 mm. Fourth layer it is 8 mm. Fifth layer it is 6 mm. Sixth layer is 5 mm, and seventh layer is also 5 mm. So uh, your calculation suggests that you can use thickness for various layers in this way. You can appropriately combine these thicknesses. You can use appropriate combinations of thicknesses to construct the shell. For example, first two layers could be of 12 mm thickness. You can suggest that first two layers, they will be made up of thickness of 12 mm. Then you can suggest that the next layer number 3 and layer number 4, they may be made up of thickness of 9 mm, whereas rest all layers, they can be made up of plates with thickness 6 mm. So in this way you can have plates of 3 different thicknesses for constructing the shell for the storage vessel. So I hope you have understood how to calculate thickness at various heights. Uh, hydrostatic pressure is changing. In this case, since we are designing it as a non-pressure tank, hydrostatic pressure will the only component that will contribute to internal loading, and accordingly the same is considered for calculating thickness at various heights. So that ends our design for the shell, where we have calculated thickness for plates at various heights. Let us continue with our discussion. Okay, one more thing that you need to calculate, and that is you have to take care of overlapping. Now let us understand that. So now you have 7 layers. Each layer is having a height of 1.8 meter. So total height, if this is the case, it will be simply height of one layer into number of layers. That comes out to be 12.6 meter. But the height of the tank is to be 12 meter. That means over here you have additional 0.6 meter height. What to do with this extra height? Let us understand. The extra height is the total height which we calculated, 12.6 meter minus height of the tank, that is 12.6 minus 12, which comes out to be 0.6 meter. So this extra height we are going to use that height for overlapping of layers. So for each layer there will be one overlapping. So number of overlappings, how can you calculate? A number of overlappings, that is NO, is number of layers minus 1. So there will be total number of layers minus 1, that many overlappings will be required. So in this case number of overlappings is 7, and if you deduct 1 from that, number of overlapping will come out to be 6. So overlapping per joint, how to get that? So overlapping per joint will be the total extra height divided by number of overlaps. Total extra height is 0.6 meter, number of overlappings are 6, so it will be 0.6 by 6, that comes out to be 0.1 meter, which is nothing but 10 centimeter. So between each layer, one layer will be overlapped with the other. First layer will be overlapped with the second layer, and the overlapping distance will be 10 centimeter. So you also have to do this calculation. Okay, so that ends our discussion for design of shell. Now let us talk about design of a self-supporting conical roof. For that, first we need to calculate total load on the roof. First you need to calculate weight per unit area of the roof. How are you going to calculate it? Let it be W. So that will be thickness of the roof into density of the material of the roof. Thickness we don't know, we are going to calculate. Density of the material is given to us. So thickness, TH is thickness of the roof, and rho m is density of the material, roof material, which is given to us as 7700 kg per meter cube. Okay, so if you just look at this equation, if thickness is in meter and density is in kg per meter cube, so you'll have unit of kg per meter square. Okay, so this is nothing but weight per unit area, which will be ultimately converted to pressure unit. We'll come to know. So therefore W will be equal to TH into 7700, that is W is 7700 into TH. So that is weight per unit area of the load. Now let us calculate load due to this W. We are calculating load due to the weight per unit area of the roof. So it will be W into G. So that is 7700 into TH, which we calculated over here, into 9.81. So that comes out to be PW is 75537 into TH, and unit will be Newton per meter square. Okay, now total load will be equal to the superimposed load, which is given to us, plus PW, which we calculated just now. Let me erase this for your understanding. Total load, let us denote it as P, and this will be superimposed load plus PW, which just, so superimposed load is given, it is 125 kg per meter square. So SI will be 125 into 9.81 if you have to convert it to Newton per meter square, and that comes out to be 1226.25 Newton per meter square. Therefore total load P will be addition of superimposed load, that is 1226.25 plus 75537 into TH. So this is the total load that has to be considered, total load that acts on the roof, and that will be considered for calculating the thickness. Okay, so we just calculated or we got total load, had denoted it as P, but let me denote it as PT. So PT stands for total load that is acting on the roof. Now let us do the calculation for the thickness for this total load. Now task is thickness for the roof for the permissible slope. What is the permissible slope that is given to us? Permissible slope given to us is 1 in 5. That is tan theta is 1 upon 5, which is 0.2. So if you calculate theta from this, theta will be tan inverse of 0.2, and which comes out to be theta as, which gives us theta as 11.31 degrees. Now the equation to be used is this one. I have discussed this equation in my video on design of self-supporting conical roof. You please watch that video for understanding this. So the equation is, for now, please know that the equation is sin theta is equal to 2.28 into dh upon th into pt upon e raised to 1 by 2 into 1 minus mu square raised to 1 by 4. dh, that is the diameter of the roof, which in case is equal to diameter of the shell, internal diameter of the shell. It is 20 meter that is given to us. So that will be the same for a roof. DH is 20 meter. PT is the total pressure which we just got. It is 1226.25 plus 75537 TH. We just got the total load. PT stands for total load that is acting on the roof. E, modulus of elasticity is given to us. It is 2 into 10 to the power 6 kg per centimeter square, but you need to convert it to Newton per meter square. So how are you going to do that? That will give us E as 2 into 10 to the power 6 into 10 to the power 4. Now this is kg per meter square. Centimeter square converted to meter square by multiplying with 10 to the power 4. Now kg will be converted to Newton per meter square by multiplying with 9.81, acceleration due to gravity. Therefore E will be 2 into 10 to the power 10 into 9.81, that will be Newton per meter square. So that gives us E as 1.962 into 10 to the power 11 Newton per meter square. Mu, the Poisson's ratio is given 0.33. Now we are going to use these values in this equation to get the value of theta. Theta is given to us, and for given theta we are going to calculate thickness for the roof. Okay, so from the previous slide you had the equation. Now I am putting all the values. So this is sin theta is 11.31, that is equal to 2.28. Diameter is 20 divided by th. PT is 1226.25 plus 75537 th divided by E is 1.962 into 10 to the power 11 raised to 1 by 2 into 1 minus mu is 0.33. So 1 minus 0.33 square raised to 1 by 4. So if you simplify it, you are going to get this equation. So sin 11.31 is 0.196. So this will be, after putting all the values, you'll be getting the equation. You just have to simplify it to get the value of th. So ultimately you'll be getting this equation. So if you simplify it, you'll be getting an equation that will be quadratic equation in th. So ultimately we'll be having this equation, th square minus 0.02 th minus 3.2 into 10 to the power minus 4, that is equal to 0. Now our task is to solve this equation to get the values of th. There will be two values for th since it is a quadratic equation, and you need to discard the absolute value and you have to select the real value for thickness of the shell. Now thickness for the roof. Okay, so we just got the quadratic equation, th square minus 0.02 th minus 3.2 into 10 to the power minus 4. You need to solve it, and you have the formula for solving a quadratic equation. If this is the quadratic equation, ax square plus bx plus c is equal to 0, then the two roots are given by this equation, minus b plus minus under root of b square minus 4 into ac divided by 2a. So I have used that equation over here. So therefore th will be minus uh, b is minus 0.02, so minus 0.02 plus minus under root of 0.02 square. So it will be square minus 0.02 square, because b is minus 0.02, so minus 0.02 square minus 4 into 1 into c is minus 3.2 into 10 to the power minus 4, and a is 1, so it will be 2 into 1. So this will be this is minus 0.02 square. Okay, so minus 0.02 square is it will be a positive quantity. That is a different thing. So after solving all the after putting all values and doing calculations for this, you get this value in the square root, under the square root. So this is minus 0.02 plus minus square root of 1.68 into 10 to the power minus 3 divided by 2. So th will be equal to, after simplifying, you just have to simplify. One root will be with positive sign and the other root will be with negative sign. So after simplifying, you'll get th as th is equal to 0.02 plus 0.041 by 2, and th is equal to 0.02 minus 0.041 by 2. So th will be 0.03 meter, or it will be 0.0105, but 0.0105, but this is a negative value and thickness cannot be negative, so we are going to discard it. We are going to continue with this. Okay, so for the permissible slope, you have got, just a minute, let me for the permissible slope, before I proceed, let me talk about the previous calculation. So at the end of previous calculation, we had got th as 0.03 meter, and the other value was negative, and we have discarded that. Okay, so for the permissible slope, you are getting a thickness of 30 millimeter, and that is quite big thickness. So you cannot go with a thickness of 30 mm. If you are using slope, the permissible slope that is given to us 1 in 5, you have to go with thickness of 30 mm. Now what we will do, in the standards, minimum thickness that is recommended for self-supporting roof, not minimum, maximum thickness. Maximum thickness that is recommended for self-supporting conical roof is 12 mm. Now what we will do, for this particular maximum thickness, let us say that we will be using the maximum uh, permitted thickness, 12 mm. So now we will calculate what will be the slope for this thickness, and if slope comes within the permissible limit, we are going to go with thickness of 12 mm. Okay, for now we cannot use a thickness of 30 mm. That will be a quite big thickness, because maximum thickness allowed is 12 mm. So not acceptable, as maximum thickness is 12 mm. So what we will do next, check the slope of the thickness, slope of the roof for thickness of 12 mm. So theta is calculated by using sin theta is, we know this equation. All values are known to us. You just have to put the values. So I'll rewrite those values for you. So all values are given to us. PT. Now PT will be total load will be calculated for the thickness of 12 mm. So for the thickness of 12 mm, you are going to get total load as 2132.69 Newton per meter square. So okay, so let us continue with our calculation. Slope, we are calculating slope for the maximum allowable thickness of 12 mm. So from the previous slide, you had this equation: sine theta is equal to 2.28 into dh upon th into pt upon e raised to 1 by 2 into 1 minus mu square raised to 1 by 4. dh is 20 meter, e is 1.962 into 10 to the power 11 Newton per meter square, mu is 0.33. Total pressure we calculated for a thickness of 12 mm, that is 2132.69 Newton per meter square. Therefore, after putting all these values, you get sine theta is equal to 2.28 into 20 by 12 into 10 to the power minus 3 into 2132.69 divided by 1.962 into 10 to the power 11 raised to 1 by 2 into 1 minus 0.33 square raised to 1 by 4. Therefore, sine theta is equal to, after simplification, it will be equal to 2.28 into 1666.7 into 1.04 into 10 to the power minus 4 into 0.972. That is, sine theta comes out to be 0.384. That is, theta comes out to be 22.58. That is, tan theta is 0.42. So for the maximum thickness of 12 mm, thickness comes out to be, the slope comes out to be 0.42, but permissible slope is 0.2. Maximum, at the most, it can be 0.2, and this is not x. Okay, so previously from the previous slide we got theta as 22.58, that is tan theta is 0.42, but acceptable value of tan theta is 0.2. Maximum it could be 0.2, it has to be less than 0.2. Therefore, what you have got with 12 mm is far greater than acceptable. So self-supporting conical roof cannot be used in this case, and what you have to do, you have to recommend a column supported roof for this particular storage tank. So in this way, you have to do design calculations for self-supporting roof. You have to take care of the permissible roof, and you also have to take care of the maximum allowable thickness for the roof. Next is, we will be designing a flat bottom. So flat bottom is constructed. We are going to construct bottom as suggested in the given data. Same plates are to be used. Plate size is 6300 mm by 1800 mm. So the maximum stress due to liquid in the tank is given by this equation. You can refer my discussion on design of flat bottom. Link is given in the description section. So maximum stress is F max is equal to pH into b square upon 2 tb square into 1 upon 1 plus b square upon a square. F max is the maximum permissible stress, which we have calculated earlier in Newton per meter square. It is 13930.2 into 10 to the power 4 Newton per meter square. pH is calculated. This time you have to calculate at the bottom. You'll have to consider the entire height of 12 meter. So pH will be calculated as H into rho into G, which comes out to be 12. Height is 12. The entire height of the tank is 12. Density of water is 1000 into 9.81. This gives us pH as 117720 Newton per meter square. A, this the longer side of the plate, it is 6.3 meter, and B is the shorter side of the plate, it is 1.8 meter. So if you put all the values in this equation, you get this equation. Now your task is to find out TB. You just have to simplify it. So after rearranging, you get equation for TB square. TB square is equal to 117720 into 1.8 square divided by 2 into 13930.2 into 10 to the power 4 into 1 upon 1 plus 1.8 square divided by 6.3 square. Okay, so let us continue with our calculation. From the previous slide, we had this equation: TB square is equal to 117720 into 1.8 raised to 2 divided by 2 into 13930.2 into 10 to the power 4 into 1 divided by 1 plus 1.8 square divided by 6.3 square. Therefore, TB square will be 1.369 into 10 to the power minus 3 after you simplify this into 1 upon 1 plus 0.082. Therefore, TB square will be 1.26 into 10 to the power minus 3, which gives us TB as 0.035. That is, thickness for the bottom will be 35 mm. So for given conditions, that means for a storage vessel of height 12 meter in which water is filled up to 12 meter, we need a bottom whose thickness is 35 mm to support that weight. So you have an option. You can use a plate of lesser thickness and a segmental ring to construct the bottom. So for time, or for now, for supporting that much weight of the liquid, we need a thickness of 35 mm. So with this, I end my discussion on this design problem. So here I have discussed how you can design shell for the storage vessel, how you can design a fixed self-supporting conical roof for the storage vessel, and if um, it is not adequate, how you can recommend the other type, that is column supported conical roof. Thanks for watching my videos. Do subscribe to my channel, do like my videos, tell your friends to subscribe to my channel, keep watching my videos on my YouTube channel to know more about chemical engineering. Thank you for being with me. Have a nice day. Bye bye.